Brakes are used to resist torque from an output shaft. As a rule of thumb, brakes are used in systems that usually require a motor start and stop 10 times or more in a minute. Brakes work on the principle of friction, which allows for rapid stops. If motors could stop rapidly, there would be no need for brakes. To see how a brake operates, we will construct a simple machine system without a brake. The flywheel, connected to the motor shaft, acts as the load to be stopped. Since motors cannot stop the load when turned off, the load of the flywheel will coast to 0 RPM. If rapid or precise stopping of a load is required, the motor cannot control either of these functions. This is an immediate indicator that a brake is needed to stop the load at a rated speed. We will now construct a simple machine with a brake attached. Again, the flywheel, connected to the output of a disc brake, acts as the load to be stopped. The brake provides resistance torque to stop the flywheel connected to the disc. As the motor is turned off at full rated speed, the output disc continues to coast. As the brake is engaged, the friction between the two discs resists the torque from the output. As the discs engage, they may have to slip a great deal before the flywheel comes to a full stop. Heat will be generated by this slipping action, but friction brakes are designed to dissipate heat. As the flywheel slows in speed, the discs will slip less and less. Finally, they will lock into positive mechanical stop. For general-purpose brakes, disc brakes are the most common. The basic components of a disc brake are the solidly mounted brake disc, friction lining, output disc, and hub. The disc's brake function is to resist torque from the brake disc to the output disc and hub. The disc brake can be manufactured with either pneumatic, hydraulics, electric, or manual controls, and the discs can be single, double, or multiple plate. The brake is configured in such a way that when the brake disc is actuated, the brake disc and output disc engage, thereby linking the two discs. When the brake disc is disengaged, the output disc will spin freely. The disc brake comes in either shaft, flange, or foot mounting. Before selecting a brake, the resistance torque at the brake location must be determined. To determine the torque, you will need to know the motor horsepower, HP, and shaft speed at the torque location, RPM. The motor overload factor does not apply for brakes. Torque in foot-pounds equals horsepower times 5,250, a constant, divided by RPM. If a 2-horsepower motor operates at 1,800 RPM, the torque would be 5.83 foot-pounds. If there is a choice of location for a brake, select the highest speed shaft. The higher the speed, the smaller the brake. The simplest, most reliable type of brake is the band brake, also called the strap brake. The brake consists of a rotating drum connected to the input and output shafts, and a flexible steel band lined with a friction material. A mechanical linkage tightens the band around the drum. If the pull on the band actuation is in the direction the shaft is rotating, the brake is termed self-energizing. In other words, the shaft motion contributes to the actuation force. Even though band brakes wear unevenly and dissipate heat slowly, they are frequently chosen for applications calling for occasional high-energy stops. Applications would include backstops on elevators and hoists and emergency brakes on vehicles and equipment. Non-friction electromagnetic brakes employ electromagnetic attraction to resist torque. These types of brakes are primarily used in applications that require variable slip. Electromagnetic units excel at soft stopping and are well suited to remote and/or computer control. They cannot, however, be called upon for rapid stops. Electromagnetic brakes require a source of electric power and are not as compact as friction brakes. The basic components of a magnetic particle brake are the rotor connected to the input and output shaft, stationary housing, magnetic particles, and electromagnet. The magnetic particles, similar to iron filings, are located in the space between the rotating disc and the stationary housing. Without any voltage and current, the particles sit in the cavity. When voltage and current is applied, the electromagnet coil is energized. Magnetic flux lines span the cavity and try to bind the particles together like a magnetic particle slush. As the voltage and current is increased, the magnetic field increases, strengthening the bind of the particles. The brake rotor passes through these bonded particles, causing drag during rotation. The output of the housing is rigidly attached. As the particles start to bind together, a resistance force is created on the rotor, slowing and eventually stopping the rotor and output shaft. The degree of particle bonding is directly proportional to the voltage and current and determines the level of torque resistance. When the current voltage is released from the brake, the rotor is free to turn with the shaft. Magnetic particle brakes are useful in tensioning and positioning applications in which speeds are continually changing. At zero speed, this type of brake holds well, but in slip conditions it tends to generate considerable heat. Applications would include packaging and printing machinery, conveyors, and factory automation. Hysteresis brakes are constant torque devices. They are made up of an output with a hysteresis disc drag cup and an input motor with an electromagnet, which is solidly mounted. When current voltage is applied to the electromagnet, it creates a magnet flux field. This flux passes into the rotor portion of the field. The hysteresis disc physically passes through the rotor without touching. These discs have the ability to become magnetized depending on the strength of the flux. As the rotor rotates, magnet drag between the rotor and output hysteresis disc takes place, allowing for constant drag or eventual stoppage of the output shaft. The resistance torque is proportional to the coil current voltage. When the current voltage is released from the clutch, the armature is free to turn, and no relative force is transmitted between either member. Hysteresis brakes have precise control, suffer very little wear, and offer almost unlimited service life. They excel in wide torque ranges. Applications would mostly include test stands. As you have seen in the previous sections on clutches and brakes, disc brakes and clutches do not differ very much in form or appearance. However, they do differ in tasks they perform. Clutches transmit torque. Brakes resist torque. To see how a clutch brake operates, we will construct a simple machine system with a clutch and brake combination. The flywheel connected to the brake acts as the load to be driven and stopped. The motor connected to the input disc of the clutch provides the input torque to drive the flywheel. The output disc of the clutch is connected to the input of the disc brake. As the motor turns at a full rated speed, the input and output disc are engaged. The friction between the two discs transmits torque from the input to the output, which turns the flywheel. When the clutch is disengaged, the motor continues to turn at a full rated speed and the flywheel continues to coast. As the brake is engaged, the friction between the two discs resists the torque from the output, which is connected to the flywheel. As the discs engage, they may have to slip a great deal before the flywheel comes to a full stop. Finally, they will lock into a positive mechanical stop. In clutch brake terminology, a cycle is one start and one stop. These start and stop cycles are usually counted over a 1-minute duration. An electrical motor is also measured in cycles. For a motor, the cycle rate is based on rated speed and stopping time over a given period. Let's look at a typical motor stop-start cycle. The gradual upslope at the start indicates the time required for the motor to build up to rated speed. The gradual downslope at the end indicates the time required for the motor to stop. If we run the motor continually and engage and disengage the load with a clutch, the curve looks something like this. You can see we have significantly decreased the time to start. However, we have not decreased the time to stop. Now, if we run the motor continually and engage and disengage the load with a clutch and brake combination, the curve looks something like this. You can see a significant decrease in the start and stop time. In other words, a clutch brake used with a motor will increase the number of cycles per hour a machine can produce. Another advantage of the clutch brake is the ability to start and stop a load accurately or in the correct position. Disc clutch brakes are the most common for general-purpose clutch brake combinations. Their basic components are the input, clutch lining, clutch disc, brake lining, brake disc, and output. The function of the clutch brake is to transmit and resist torque. The disc clutch brake can be actuated with pneumatic, hydraulic, electric, or manual controls. The discs can be single, double, or multiple plate. With all clutch brake combinations, the clutch should be on the input and the brake on the output. Flange mounting has become popular because it is quick and simple to connect. It does not require belts, pulleys, etc., and usually does not require couplings. It is usually compatible with NEMA C-faced motors and gearboxes. Electromagnetic clutch brake combinations operate in the same manner as in the clutch and brake sections. The most common types are magnetic particle and hysteresis. They generally do not come in packaged sets, but must be mounted individually as the clutch and brake. Again, it is important to remember that with any clutch brake combination, the clutch should be on the input shaft and the brake on the output shaft.